7, 8, and 9 now are going to have you prove the trigonometric identity like we did on the previous ones, but now we have to figure out the steps ourselves. So I like to look first of all here like they did. They did Pythagorean identity first, so if I look there and see one that looks like a Pythagorean identity, that's what I'm going to do first. 1 minus the cosine squared of x is equal to the sine squared of x. Remember, that's the one where they rearranged it and said sine squared plus cosine squared equals 1. So 1 minus the cosine squared would equal the sine squared of x. We still have the cotangent of x, and we did the Pythagorean. So they're going to make you put the step and pick out which identity you used. The next thing I'm going to do, I'm going to change my cotangent. I want to change it in terms of sine and cosine. I'm going to use my quotient identity. The cotangent of x is equal to the cosine over the sine. So cosine of x over the sine of x. That's one of my quotient identities. Next thing I'm going to do is I'm just basically going to cancel. So I'm going to get sine of x, cosine of x, which is what I want to end up with. And all I did there, since I just canceled, was just straight algebra. Now I've done my proof. So again, you're going to want to have your fundamental trigonometric identities. Oh, my writing's popping up there. And for these ones, they're just going to use the reciprocal identities, quotient identities, and Pythagorean identities, along with some algebra. And again, on these, they may rearrange them in a different order and solve it. Like this one, would tangent squared would be secant squared minus 1, because I have to move this over. Those kind of things. So if I go back to problem number 8, it must be that we are on. Let me move my board up here. Again, I'm going to start out because I see that I have one of my Pythagorean identities. If I look here, I've got 1 plus tangent squared equals secant squared. So I'm going to go ahead and use that and make that secant squared of x. So cosine of x times secant squared of x, that's using my Pythagorean. And then I look and say, oh, I want to leave this in terms of secant. So I want to change this into secant. My reciprocal identity happens to be that the cosine of x equals 1 over the secant of x. And then again, my last step here, if I just do some canceling, I get the secant of x, which is what I want to end up with. And so my last step again, we're just using some algebra to simplify my expression. Number 9, I want to change 1 minus cosine squared of x times the secant squared of x into the tangent squared of x. Again, I'm going to start here, and I'm going to go ahead and use my Pythagorean identity. Sine squared plus cosine squared equals 1. So 1 minus the cosine squared of x is equal to the sine squared of x times the secant squared of x. That was my Pythagorean. It's writing in weird spots. I want to put it in terms of tangent, so I like to try to get it in terms of sine and cosine. I'm going to change my secant. My secant's reciprocal identity is 1 over the cosine. Since this is squared, it's going to be 1 over the cosine squared. So the sine squared of x is going to equal, or it's not going to equal, sine squared of x times 1 over the cosine squared of x is going to be my reciprocal identity. I should have probably left myself some more room. But here, if I do algebra, I'm going to get the sine squared over the cosine squared. I'm going to write it over here. I'm going to come up here since I didn't leave myself room. So I'm going to have sine squared of x over the cosine squared of x, just using algebra to combine my two expressions. And again, if I have sine squared over cosine squared, Sine over cosine is tangent using my quotient identity. So sine squared over cosine squared is tangent squared of x, and that's my quotient identity. So if I've got the squaring in there, my rule still applies, it's just that it's going to stay squared. Secant squared is 1 over cosine squared. Sine squared over cosine squared is tangent squared. There's my proof.